Hi, everybody. Welcome to the Aerospace Engineering Seminar Series. Thank you for coming. Today, we have the pleasure of having here Associate Professor Marco Fossati from University of Strathclyde. He's a director of the Laboratory of Future Air Transport Technology, which counts on a laboratory which counts on 5 academics and 15 among postdoctoral or doctoral researchers. Professor Fossati is active in 2 main areas. One is the non-equilibrium hypersonic flow physics, and the other one is the data-driven models for aerodynamics of non-conventional vehicles. He leads several projects, both at the European level, for example, Clean Sky, well, now it's over, but Horizon Europe, or the old Horizon 2020, he led some of them. And also he has a strong collaboration with ESA. Overall, he has been leading as PI more than 10 of these projects. He's collaborating with several famous institutions such as Stanford or von Karman Institute, and also very famous UC3M, right? We are collaborating now within a project was being selected for financed by the European Horizon Europe, within the Horizon Europe framework. Okay, Marco, I would say that the stage is yours. Thank you.
Thank you very much, Rauno. Thank you very much, everyone. Thank you to UC3M for inviting me to give this seminar. And so this slide here that I have put here, which this is Oxford, but the picture is not the one of 1942. It's a most recent one. I want to bring a little bit back in 1942 and start with what Einstein was doing when he was there teaching physics. And it happened that one of his assistants reached to him asking the question, Professor Einstein, have you noticed that the exam paper that you have just given to the students is the exact same as the year before? He says, I mean, the questions are exactly the same. And Professor Einstein said, I know, the questions are the same, but the answers have now changed. And when I think about this, I think about this episode, and I think about all the work that I have the pleasure and the luck to be involved with atmospheric entry gas dynamics, hypersonic and non-equilibrium flows. So it resonates a little bit, the fact that we are working in an area where we have been able to provide answers as engineers. So I'm not a physicist, so I don't want to put myself on that side of things, which it's a very big fight between physicists, scientists, and engineers, right? But so if you think about how engineers have been able to answer the question, so to solve problems in atmospheric re-entry, we went to the moon, we sent stuff on Mars, we have sent probes and other man-made objects all around the solar system. So we have solved this problem. So we have had questions. Last year we had a question. So we had an answer. But these answers keep changing because we are more and more interested in going forward, pushing the boundaries, and we are challenging ourselves when we talk about atmospheric entry gas dynamics. Okay, what has happened here? Well, I can leave it like this if this is okay. I don't know. This is better. To the fact that we constantly need to validate and assess the quality and the completeness of our answers. Now, why atmospheric gas dynamics is important? Because we want to survive the problem of flying across the atmosphere of a planet of a satellite or any other object that has an atmosphere. So here you see we want to go to the moon. Fine, we went there, we want to go back, but then we need to come back to the Earth and be sure that when we are re-entering the Earth's atmosphere, well, we don't fry the astronauts that are inside the capsule. But we want to go to Mars. We want to go and do many more other things within our solar systems, outside our solar system. And we need to survive all of them. And if we have an atmosphere that we have to deal with, well, we have the problem to understand how to deal with the very high loads that come from very high heat fluxes, very high temperature, a lot of pressure, shock waves, and so on and so forth. But we want to understand it and be better, have better answers, because we want to destroy stuff. So, white and black, right? We want to survive, but we want to destroy stuff. And this is what we have to do, or one way that we can look at the fact that we have a lot of space junk around our Earth, our planet, and one way of getting rid of those and ensure the sustainable use of space is to make sure that we have a way to get rid of satellites, spacecraft, fragments of satellites or other objects that we have sent out in outer space or in orbit when they reach their end of life. And destructive atmospheric re-entry is a way of doing it. So it's a way of picking up a satellite that no longer works, make it re-enter in Earth's atmosphere, and ensure now that the heat fluxes, the pressure loads, and anything that goes on is enough to destroy. Because we don't want fragments hitting the ground, possibly hitting people, and having unpleasant consequences. So that is the why. But what is what? So what is atmospheric entry gas dynamics? So this is a topic that has been studied for many years, many decades, by many people, many researchers and scientists. And I am not here just to say, this is what it is. What I want to do here within this seminar is just to, first of all, agree on a little bit of the terminology, the words, the jargon that we're going to use, such that we can understand each other, and to touch some elements of atmospheric planetary entry gas dynamics that are relevant for the type of research that we do in Strathclyde, with the European Space Agency, with other collaborators. So, I have taken the liberty, which again, it's not a rigorous definition, it's not a theorem, but I've taken the liberty to characterize or to give my answer to what is atmospheric entry gas dynamics as something, as a discipline that has to deal with high temperature, high Mach, non-equilibrium flow physics. So it's high temperature because when an object is re-entering on Earth and is now flying at very high speed, very high Mach number. Now Mach number is not speed, they're not the same thing, okay? There is the temperature, the speed of sound between, but again, let's try not to be too picky and too theoricist now. The very high Mach and the very high speed triggers a number of aerodynamic effects that induce a lot of aerodynamic drag on the vehicle, and as a consequence of this, there are very steep gradients of a number of quantities, but especially temperature. And so in the surrounding, if you go very close to the surface of the object, you have a very high temperature, orders of thousands of Kelvin, okay? It's high Mach because, again, if we want to re-enter from a planetary trajectory, if we are re-entering from the moon, if we are re-entering from Mars, we are typically flying very fast. Very fast because, well, you need to go outside very fast, but also because at a certain point, as you approach the Earth, the gravitational pull is accelerating the object, and so you see that you are accelerating. And you want to be sure that that acceleration is not doing you more harms than goods. And it is non-equilibrium. Non-equilibrium for various different reasons, but I would like to mention two, and I will explain and I will explore more one of the two. There is non-equilibrium because when we are flying in the higher layers of the atmosphere, the density of whatever is the gas that is making the atmosphere is low. Or better, the number density, which is the number of particles, of molecules per unit volume, tends to be very low. And so all the equations that are the classical equations that we tend to study at school, that govern the fluid mechanics, the Navier-Stokes equations and so on, are not very correct. Because those equations have the assumption that the gas is sufficiently dense, the hypothesis of continuum. We have to have that. Otherwise, the Navier-Stokes equations don't work well, meaning that all the predictions that we do, pressure, temperature, velocity, aerodynamics, heat fluxes, and so on, are not very good. And that's one type of non-equilibrium, because the molecules are apart, and therefore it takes more time for them to collide, and therefore if we have a perturbation, whatever it is, due to the presence of an object or something else, it takes a little bit of time to reach equilibrium, because there are not so many collisions, there are not many particles. But it's still non-equilibrium also because the object flies very fast. So the residence time, the characteristic fluid dynamic time, tends to be very small. So the time that a certain element of fluid, and now we can assume that we are in the lower layers of the altitude, so of the atmosphere, so the atmosphere is dense enough to have this hypothesis of continuum valid. But the speed at which those vehicles are flying, or if you change the reference frame, at which the molecules are hitting the object, is very high, and therefore the time is not a lot. And even if now you have a lot of molecules that are colliding, still the time that they have to collide and then to reach equilibrium, to a relaxation process, is not very high. And so you are in non-equilibrium. Here on the left, you have a summary of all these things brought together. It's a capsule that is re-entering the atmosphere, and the usual very specific terminology, very specific flow physics, shock wave, shock layer, high temperature effect, separation, radiation, plasma generation, ionization, and so on and so forth. This calls for the fact that anytime we want to deal with atmospheric gas dynamics, it is an inherently multi-physics problem. It's not fluid dynamics only. It is fluid dynamics, but you have chemistry, because at certain high temperatures, air is no longer inert. You start having chemistry. So at 2000 Kelvin, molecules of oxygen, O2, starts dissociating. O2 starts dissociating. At 4000 Kelvin, nitrogen starts dissociating. And if you reach temperatures such as 9000 Kelvin-ish, you start having ionization. Electrons are split away, and you have positive ions, you have electrons, you have plasma, you have MHD, magnetohydrodynamics, magneto-gas dynamics, because then you have electrons moving around your vehicle, and that induces currents, magnetic fields, and that is another very complicated, very multidisciplinary problem. So the outline, so I spent a lot of time just to come to the outline, but at least we have set a little bit the context here. I have 4 parts here, and again, this is by no means a talk that has the ambition to cover everything. It's impossible, right? So what I will do with these 4 parts is that I will try to guide you through some key concepts about continuum regimes. We're not talking about non-equilibrium for rarefied flows, so we discard that. We are now in the continuum regime. But want to go into a little bit of the flow physics, the theory, gas kinetic theory, that is instrumental to understand some important phenomena that we will be discussing later on. And then I will go with part 2 and part 3, looking at 2, I would call them applications, but let's say areas where we are studying, in one case, some fundamental problems, shock interference patterns, and in the other case, a little bit more an applied problem, even if that's, again, a terminology that is destructive atmospheric reentry. And then I will close with a little bit of perspective, where we are going, what is the people doing, what are the scientists in the world doing, what is the most important questions that we need to ask now, or is there any question that has an answer, but that answer needs to be improved, needs to be corrected, completed. So let's start with part one. And I would like to start with bringing your attention to the fact that when it comes to gas dynamics, and gas dynamics in these conditions that we've been dealing with, we cannot neglect the fact that the molecules have a structure. And if you have a molecule with two atoms, O2, molecular oxygen, well, the way energy can be stored in this energy is different than what happens in the way that energy can be stored in an atom of argon, for example. Because we have two atoms of oxygen, one chemical bond, and therefore this object can rotate, okay, but can vibrate. And so this idea of having an internal structure of the molecules is what leads to the fact that when it comes to the internal energy that the thermodynamics book keep telling us that there is an internal energy, that internal energy is not only, well, a translational energy of a particle. That works if you are dealing with less complex flows, and you have that each molecule of the gas is a billiard ball, and then you can treat just the internal energy as its translational energy. But in reality, due to the high energy levels involved into atmospheric reentry, well, when two molecules collide, well, that energy has to go somewhere, and it doesn't go only in an exchange of translational energy, exchange of momentum. It goes into vibrational energy. So the molecule starts vibrating like if there was a spring between the two atoms, and it starts rotating. And there is also the fact that we have electrons that make these bonds, and if we have more complex molecules, are surrounding with orbitals the atoms that we have, and so on and so forth. And the energy level at which these electrons find themselves depend on the energy that is involved into the collision. And so electrons can change their electron level if the collision is sufficiently high. And that's why we need to account for these mechanisms if we want to have a good and accurate prediction of what it is happening. And we will see, I will show an example of why this is important. What is the difference? Now, this is the microscopic world. Okay, again, I could go much more into the detail of it, but right now I just want you to focus on this idea that if we're looking at atmospheric gas dynamics, we need to deal with the internal structure. We cannot deal with billiard balls. It doesn't work. What we do to pass from this world, which is the microscopic world, where we have a super focused telescope that looks at the various particles, to the macroscopic world, that is what we feel, because we have a certain dimension, right? Is a bunch of integrations. Now, I'm making it very simple, right? But the point is, you can describe the kinetic of these molecules, the dynamics of these molecules, and then the way you go from there to the macroscopic world, so the classic Navier-Stokes equation, is by making a lot of integrals, complicated integrals of these microscopic quantities. But at the end of the day, this is what you have, okay? And this that I'm showing here is just one example with a very specific set of assumptions behind the behavior of the gas and behind the way we carry out those integrals I was mentioning before. So what you have here is a macroscopic set of conservation equations for the fluid mechanics. So the system of equations that you see at the top in vector form and with the split that you see in the central part is essentially stating conservation of mass, Newton's law, and the principle of thermodynamics. So conservation of mass, momentum, and energy, but with the distinction, with the notable difference that now, if you look at the two equations at the bottom, we have two energies, okay? And this is a consequence of one of the assumptions that I made before on the basis of, not that I made before, that I mentioned before, that looks at the fact that we have different internal degrees of freedom in our molecules, and one way to deal with those is to assume that molecules have an internal structure such that the internal energy associated to translation and rotation are in equilibrium, and the internal energy associated to the vibration and the electrons are in equilibrium. But the presence of these two separate, let's say, energies means that we need to deal with one more equation for the energy as opposed to the standard Navier-Stokes. And this is the last one that you see at the bottom. That is the conservation equation for the vibrational energy assumed in equilibrium with the electronic energy. So we simply talk about vibrational and electronic energy. And that is for unit volume, okay? While the second last is the conservation equation for the total energy per unit volume. Total energy means internal energy, means kinetic energy, now the bulk one, vibrational, rotational, and electrons. They're all there, okay? But this is already a step forward with respect to the classic Navier-Stokes equations. And what you see is that if you look at the fluxes, so the two central terms with an F, you have convective fluxes, so transport, okay? You have viscous terms of diffusive fluxes, so whatever you have effects of viscosity, thermal conductivity, heat fluxes. And if you look at the top equation, we have diffusion. That's because now you don't have only one equation that states the conservation of mass, but you have to write one single conservation equation for mass for every species in your gas. Okay? Now, since we are expecting to observe and we want to observe chemistry, we need to deal with the species that we have. Air is not air, period. It's made by oxygen, nitrogen, argon, and a bunch of other traces, right? But typically, you can go ahead with nitrogen and oxygen. And so you need to write a conservation equation, partial density. So rho with a subscript is a partial density. So the density of a species divided by the density of the full mixture. And you have the transport of it, second term, vertical. And then you have the diffusion. When you have gradients of the concentration, as a consequence of that gradients, there is a diffusion process. Okay, even if everything is not moving, if everything is still. And then at the very right-hand side, you have source terms. Typically, you look, or you might have seen Navier-Stokes equations that are homogeneous. There is zero on the right-hand side, right? Yes, you can put gravity there, you can put other stuff, but typically you don't. But now, we need to have source terms because we have the production, the destruction of species as a consequence of the chemistry that is going on. If we think about O2, so molecular O2, if we have a gas at above 2000 Kelvin, that O2 dissociates into two atoms of atomic oxygen. And so we need to have, if we want to address this mechanism, one conservation equation for O2, one conservation equation for atomic oxygen. And the moment we dissociate O2, we have production of O2, right-hand side positive, and destruction, of atomic oxygen, and destruction of O2 on the other side. And it is very important that we take into account this chemistry, because if you don't, all the energy that would have gone into breaking the various chemical bonds would have been revealed as sensible energy, so as temperature in the gas flow. And this means that if we were to simulate the re-entry of the Apollo capsule from the moon without accounting for those, you would have temperatures that are incredibly high. Tens and tens thousands of Kelvin, that it's not realistic and that it will be very difficult to to face with the materials that we have now, unless to do something very heavy. That doesn't work as well. At the bottom part, you have the thermodynamic equations that are needed to complete the set of equations, balance between unknowns and equations. So you have the thermal equation of state for pressure, Dalton's law. Then you have definition of what is the source terms. Again, that's chemistry. Okay, production, destruction, species, stoichiometric coefficients going on there. Constants of reaction at the very right-hand side. Arrhenius law is typically what we do, but with Tc now, Tc is a characteristic temperature that now has to deal with the fact that we have two energies, two temperatures. And so there are functions there. And then below, classic equation for shear stress and the heat flux for each one of the energies that we have. So to complete, we need a caloric equation of state, that is the one that allows us to define what is the internal energy, okay? And so we have an internal energy with an internal structure with the first term that is translation, the second is rotation, vibration, electron, and the ground state. So you know that internal energy is a function of state, okay? So it doesn't matter its value, but its value with respect to a reference state. And what you have here is that you have to have these for every single species. For oxygen, for nitrogen, atomic nitrogen, nitrous oxide, and so on and so forth. Now, I don't want to annoy you again much more with this slide here. Too many equations, I know I don't like them. But what I want to draw your attention here is on one specific thing, and is the chart on the left-hand side. Now, forget the intermolecular potential and interaction, don't care about that, but I want to bring your attention to the fact that we are dealing with internal energy modes that are quantized, okay? Quantum mechanics, woo, Einstein, right? So that is the fact related to the fact that we have packets of energy, right? And before having that certain amount of energy goes actually into vibration, we need to reach a certain level of energy, right? So if you do not have collisions that are sufficiently energetic, okay, the energy is not super high, well, you will not have that your molecule will vibrate. And so you can go back to your billiard ball model, because now whatever it matters is kinetic energy, so translational energy of your molecules, because the collisions are mild, okay, and you don't get them to vibrate because the stiffness of the spring you have in your idealized harmonic oscillator model is too strong, and then it really doesn't move. There's no appreciable energy there. But if the collision starts becoming more intense with higher energy, higher momentum to be exchanged, then you start having this vibration. Now, where all this is going? Well, not much about quantum mechanics, but about the fact that usually, that's the message, when we are dealing with an internal structure of the gas, of the molecules of the gas, you tend to populate first the translational and rotational modes before having some amount of energy stored in the vibration of the molecule, okay? So there is a sequence of events, and that is why we tend to go with a two-temperature model, because we say, you look, translational and rotational tend to reach equilibrium very fast. You see, all those energy levels are very close, so there is the need of a very small amount of energy to go from one level to another, and that reaches equilibrium relatively fast. That is not what happens, for example, with vibration. You need to go with much more higher levels of energy. And if you don't get the right packet of energy, you don't go there, okay? And this is an important aspect that I will use later on. Questions? Maybe I don't know if there are questions now. Okay, so that's the theory done, so you can relax. Now it's just colorful images. And we can go ahead with this. So the first thing I want to show you is some work that we have been doing in trying to define the way shock waves interact in non-equilibrium conditions. Why this is important? That's one example, one of the many. because you might have somewhere locally in your object that is re-entering the presence of multiple shock waves, maybe some generated by the nose, some other generated by a control surface that is now activated and deflected and so on. And the outcome of this mechanism of interaction is important to be understood well. First of all, because it's important we understand things. Okay, it's important that we advance knowledge. But it is also important because you don't want to have an increase in pressure or an increase in heat flux so high that will destroy your control surface. If you destroy your control surface, if you destroy your thermal protection system, you have that your astronauts will become Kentucky Fried Chicken. You don't want that. Okay? And here I have made the statement about two different models that we may want to consider. One, the one at the bottom, is what I have been annoying you with the questions before. Two-temperature model, multi-species, finite rate chemistry, and so on and so forth. The one above is something that is the, I would say, most immediate step after the classical Navier-Stokes equations. And let me open and close a parenthesis here. Whenever I talk about Navier-Stokes equations, I intend mass, momentum, conservation, total energy per unit volume. There are out there, and I'm not saying it's right or wrong, I'm saying that's the language I use, people who say Navier-Stokes is just momentum, because they think it's incompressible, so mass, it's incompressibility constraint, we don't care about that, there's no thermodynamics, and we just deal with momentum. Okay, fair enough. I talk about Navier-Stokes as the full set of 5 equations in the classical fluid mechanics, which is parabolic incomplete for those who like mathematics. But we can talk about this later on. Now, so the immediate step afterwards is thermally perfect gas. What is a thermally perfect gas? Is a gas that is still very close to the perfect ideal gas, the one you study with the classical Navier-Stokes, but with the fact that now the specific heats, constant pressure and constant volume, are no longer constant, but they vary with the temperature. And this is a first approach you can use to introduce the fact that the molecules have an internal structure. Because the change in CP is a consequence of the various activation of the internal degrees of freedom. So you are populating vibrational modes, electronic modes, and so on and so forth in a way that is different, that is in non-equilibrium with respect to the translational and rotational ones. And what we want to do is essentially this. We want to be able to define a schematic for the different types of interaction between shock waves. Everything started in the 60s, 1960s, with a guy called Edney, who studied the interaction of an oblique shock with a bow shock in front of a cylinder, and noticed that if I change the location at which the oblique straight shock interferes with the curved shock before the cylinder, the outcome of this interaction is very different. And he found out 6 different types of interaction. So there are some of them that are more simple than others, but the ingredients is that you have shock waves, you have shear layers, okay, so layers of fluid that move with different velocity, and there is a shear. There are contact discontinuities that are, again, the ideal word of, they are counterpart of shear layers. There are rarefaction waves, there are jets, supersonic jets, and so on and so forth. And then from that seminal work, people have applied that to double wedges, to other configurations, such as double cones, and that's what we want to do. We want to be able to identify schematics like those that you see at the top right for a wide range of different types of interaction. And what we did was to focus on CO2. Why? Well, because it's cool. Because it is the main constituent of the atmosphere of Mars. So Elon Musk should write us a check for this, but he doesn't. So this is what you can see here in terms of some results that we got when we studied the same geometry. So it's a double wedge, 15 degrees the first ramp, 55 degrees the second ramp. And this is a Mach 9 flow of CO2 and N2. That's the mixture that you have on the atmosphere of Mars. Left-hand side solution is a thermally perfect gas. Central solution is non-equilibrium gas. Now, I save you the pain on the eyes on trying to understand what is happening at the top with those numerical Schlieren. And I just want to show you a little bit what is happening in the schematics that look very similar, okay? So one would say, well, what's going to be the reason for doing all of this? But in reality, there is one tiny, teeny small thing that changes everything. But when we look at the non-equilibrium model, now let me see if I can write here. This guy here that is reflected, okay, now in this case, give rise, what's happening? To a shock wave. So there is a small shock wave here, is this guy here, that is not present here. Okay? And that shock wave has an influence on the peaks of pressure and on the peaks of heat fluxes that you will see on the wedge. Okay? And this is a consequence of the fact that we are accounting for the appropriate energy exchange between the molecules that we are not doing in the thermally perfect gas. In the thermally perfect gas, there is no concept of translational and rotational gets to equilibrium before then the vibrational one. So when we have a shock wave and we have a thermally perfect gas, all the energy is immediately converted and equally distributed throughout the entire internal mode. That's not what happens in the case of a non-equilibrium model, and because you have first energy going into the into the translational and rotational modes, and then after a while, after a relaxation process, you hit the vibrational one. What does it mean that, in terms of practical reasons? You have a shock wave that you don't have in the thermally perfect gas or in the perfect ideal gas. You have different peaks in pressure and heat fluxes. And so if you look at the black line on the rightmost side, you have that the non-equilibrium gives you the highest peak in pressure, and the shock wave I'm talking about is responsible for this jump here that is not present in the other two. And what you see, interestingly enough, and hopefully likely, that the peak of heat flux is much smaller than the one you will have with the thermally perfect gas. So if you were to design a spacecraft and use a thermally perfect gas model, you will have to make your thermal protection system much thicker. This is a colorful image just to show you the level of non-equilibrium you have in this type of flows. So leftmost slice is translational temperature. Center slide is the non-equilibrium effect, translational temperature minus vibrational temperature. And wherever there is no color, there is equilibrium. Wherever you see colors, there's non-equilibrium. And the one at the right is just pressure, because we like pressure. And you can see that for this type of flows, there is a lot of non-equilibrium going on that you will not be able to reveal if you go with thermally perfect gas model. I will go very quickly here. This is what you will have if you were to use a perfect ideal gas model, billiard balls, constant CP, constant CV. You would have an unsteady flow, while the previous cases, the interaction was steady state. In this case, you will see that the interaction of the shock wave gives rise to a very large bubble of separation, with shock waves moving back and forth, vortices going, moving, and one may say, well, okay, so this is a very interesting, very important mechanism, except that it's wrong. And so you can use it just to show colorful images, but don't use it to do any design or any study. So these are the key findings that we have observed when using this non-equilibrium model with CO2 mixtures. And again, go back to the fact that we are now interpreting correctly the mechanism of energy exchange with a molecule that is CO2, so it's a 3-atomic molecule. Okay, so it's a little bit more complicated than what we saw before. So I will not read it, but again, I will just leave it there for you to have a quick look, and we can chat about it later on. This is the second application I want to show you. Now here, differently from what we've done in the other case, our interest, well, the interest of people that work with me is at this stage developing methods. Okay, so we are developing a framework, a computational framework, to simulate the destructive atmospheric re-entry of a satellite. And the simulation that you see there is a real one that we did. Solar panels are gone, and then you let it go for a little while, and you'll see that the cap will go away, because now the pressure and the heat fluxes are destroying a number of things. So how did we get there? We get there by starting from the problem that this is, as I was mentioning before, a very challenging task. It's multi-physics, there are many disciplines, the time scales that are involved into this process are very wide, and so there's a broad range of problems that we need to address. The simulation time tends to be very long. If you want to have a good degree of accuracy, you need to go with high fidelity, and running all those high fidelity simulations takes time. And so our approach here has been to try to reduce the uncertainty that goes with this type of simulations, with the aim of improving our ability to say, look, if this object is re-entering, you have to be worried about that specific area down on Earth, because that is where the fragments will go, by developing a multi-fidelity approach that brings together low fidelity, fast, but less accurate models with high fidelity, so very accurate, but a little bit costly, in simulating everything that is going on. From the aerodynamic forces and moments, the aerothermodynamically induced heat fluxes and plasma, to the structural part of things, so how the object deforms and eventually it breaks, up to the point where we are following the dynamics with 6 DOF, so we have 6 equations for the dynamics, Newton's forces, moment, accelerations, moments of inertia, and so on and so forth. So we have a tool that is called Titan. It will be released open source very soon, so stay tuned. But what I want to do is to give you a little bit of a flow chart about the aerothermodynamic part, because my background is aerodynamics, right? So I don't do structures, I don't know what they are and how they work. But this is a little bit the way the code is organized. And if we look at the high fidelity part, so there is also the aspect of dealing with the computational mesh, with the need of refining the mesh to improve as much as possible our accuracy without spending too much time in simulating over very fine everywhere, very refined everywhere meshes. And here we are trying to go ahead with the open source mantra, right? So we are trying to use everything open source to make it something useful for the community. We are using a code called SU2NEMO. We have been developing it together with the friends at Stanford and VKI and Arizona for the continuum and slip regime, so lower layers of the atmosphere. But when we want to look at the higher layers of the atmosphere, when the rarefied regime is a little bit more intense, we go with a code called Sparta. It's done by the Americans, it's by Sandia Laboratory. All of these is brought together with some tools to do the structural mechanics. Phoenix, it's another open source tool, and all is integrated together and works. So what I want to do here is just to show you how much difference there might be in going from one method, low fidelity, to another one, multi-fidelity. On this specific case, this is a real case, right? So this is an ATV cargo, real European Space Agency vehicle. This is a simplified geometry just for the sake of a proof of concept. These are some of the conditions that we have, and here on the right you see a little bit the trajectory of the main tank, the main object that you see, the main cylinder that you see there. So what we did is, okay, how much, don't show that then this is gonna show very nicely here, but I will try to make some notes here. So the central animation shows you the fragmentation of the panels with a low fidelity method. Approximate method, very fast, you can get solutions in seconds, if not minutes. The right one is the exact same conditions, but with high fidelity. You see immediately with your naked eye the difference in the dynamics of the solar panels. And that is going to be massive if we now consider many more fragments, possibility that they collide and that they go and change the overall trajectory. Here, those, I guess now not very clear graphs shows the differences in the attitude, so roll, pitch, and yaw of each one of the panels between low fidelity and high fidelity. Now, I know this is very difficult to read. Probably I could share the presentation and this will be more clear with everyone. But for example, if you look at this arrow here, this is the delta in terms of radiance between the rotation of around the roll axis of the solar panel between low and high fidelity. Okay, and there are differences that are similar in the other cases. So it's so we are talking about. So now, if my eyes don't fail me, so you go approximately from 2.5 close to 0, so 2.5 radians, which is not that negligible. Of course, everybody would like to go and do high fidelity simulation like this one. So this is the same object now with a more detailed structure of the solar panels. We have solar arrays with joints that connect them, made with their own material. And you can see here an example of the importance of using mesh adaptation, right? Because that will allow you to reveal and capture the shock wave that is generated near the body and that will impinge on the solar panels, being the major reason for the solar panels to bend and break away. Here is the multi-fidelity result. Okay, so what you see here is a number of lines that look at the forces and acting on the various objects that you see, the various fragments that you see there being broken. And what you see in terms of comparison between the purple line and the yellow area is that some of them are done low fidelity, the other one is done high fidelity. So you see that the purple one is low fidelity, the yellow one is high fidelity. And you could see the discrepancies between the low fidelity and the high fidelity solutions, forces and moments, by comparing the lines. And what you observe here is that, of course, when you are in the high fidelity, there is only one line, that is just the CFD one. It's okay, it's fine. But when you go outside, you can see that there are substantial discrepancies. And these discrepancies arise when the objects are complex and there is shock wave interaction between the self-generated shock wave and the solar panels. But when an object goes away alone, and therefore doesn't feel anymore the influence of the other shock waves, then these graphs, these plots show you that low fidelity methods are not that bad. And so the forces and moments are quite okay. But there has to be no interference within the shock wave. And so this multi-fidelity approach is capable of automatically identifying the existence of such an interaction. And if such an interaction exists, then you go with high fidelity. Wherever you see the colored mesh and so on, that's high fidelity, because there is the interaction between the main body, the solar panel in the back, and so on. But whenever something goes away and is now alone, is by itself, then you can go ahead with low fidelity, and that works relatively okay. Of course, it's a trade-off, right? You would like to go always with high fidelity, but you can't. So you have to find a compromise. So, final part, am I right with timing or late? It should be, okay. Okay, so this outlook and perspective is split into 3 categories. Physical models, numerical models, applications, okay? So this is a list of what are, right now, as we speak, the most hot topics in the physical modeling part. I don't want to talk about turbulence. Everybody in fluid mechanics says that turbulence is important, and it is. And it is even so more when we look at these very complicated flows. When we look at the interaction between the plasma that is being generated near the object and the turbulent structures there is a scattering of certain frequencies and electrons, and that's an impact on radio frequency, how you detect things, how you communicate to the astronaut. But I want to spend a couple of words about the first one. This is a recent project that we have with ESA that just started to introduce an even more accurate way of modeling the non-equilibrium processes by doing state-to-state modeling. So all those quantized states that identify the state of the various molecules and atoms in your gas can be modeled accurately by state-to-state. It's a very costly, very expensive simulation, but that's the way people are going. Numerical modeling, well, I haven't spoken quite a lot about numerical modeling. It's boring, it's mathematics, but I just put this here because I think it's important that we have a little bit of idea of what it is happening. And so we are looking at essentially three major categories. We want to increase the numerical accuracy of our methods, DG, discontinuous Galerkin, higher order scheme. That's fine. A lot of problems with oscillations near shock waves and so on and so forth. But we want to go on the other side of the spectrum, having very low fidelity methods that we can use to make fast predictions of these complex flows, such as data-driven methods, machine learning, artificial intelligence, physics-informed neural network. That's what people have been doing now. The last one is uncertainty. Uncertainty treatment for the numerical methods, right? So it's called epistemic uncertainty. Ooh. Now, that's what looks at the fact that no matter how good you are, your numerical model and the way you solve the equations that result from your numerical model are wrong. I'm exaggerating, of course, but there is an error there. And so you want to be able to quantify that error. In terms of applications, well, there are many. But here I have identified some that are one of the most exciting, one where people is now really looking. Again, fundamental mechanisms such as the first three, non-equilibrium flow instabilities. A shear layer in non-equilibrium flow is, whenever it gets to be unstable, one of the drivers of the transition to turbulence. So if you have a nice shear layer that stays there, maybe thickens a little bit because it's non-equilibrium, but it stays there, it's fine, we're okay. But if that starts becoming unstable, Kelvin-Helmholtz instabilities and so on, that may lead to transition to turbulence and increase of its fluxes, increase of shear stresses, and everything. Gas surface interaction and plasma modeling, these are very important because you really go into now studying the fundamental mechanism of what is happening really near the wall of your object. And so if you want to design thermal protection systems to avoid the KFC outcome, well, you really want to be able to understand the presence of catalysis, ablation, multi-phase, because you might have some char that enters now your flow, and then you have particles and flows and so on, and that's very important. All to go to the two very interesting, very exciting applications about destroying something, either in a controlled or uncontrolled manner, or survive something, survive the entry in alien planets, or surviving your probe that you are sending, for example, on outer planets. So I want to close here just acknowledging a little bit of research grants that are behind all the work that you have seen, but much more that I have not shown. My hypersonic team, so the group of PhDs and RAs that have been constantly working on these specific applications. And then the SU2, Mutation++, and high performance computing. And I want to finish going back to a movie that I used to watch a lot when I was doing my PhD, not because I am that old as the movie, right? I'm not that old, even if I have white beard, but that's because I found myself to watch it a lot. So that's Apollo 13, right? You might have seen it, you might have known it. So who knows who are the two guys in the circles? Sorry? That's Tom Hanks, correct. Good job. But who is this guy? Now, you know what role was playing Tom Hanks in the movie? Tom Hanks was impersonating astronaut Jim Lovell, one of the astronauts that has one of the most experience in terms of number of flights. He was on the Gemini project, he was on the Apollo project, and he made a lot of space flights. So everybody remembers Neil Armstrong because he put the first foot on the moon, but Jim Lovell was a good guy. Well, this guy is Jim Lovell. So he made a cameo in the movie. Nobody, I mean, I know, but a bunch of other people knows, but he was really there, right? And so he is the guy that Tom Hanks was impersonating in the movie. And so that's a fun fact. Thank you for your attention.